Gigi, and welcome to week 6 of SSSSS. We've heard from 5 great teams, and in case you missed them, we'll be giving a recap of the first 4. But first, for something a little different, our team is going to present to you a project that we have been working on called Schrodinger. We created this Java library using code that we wrote last year in order to share our knowledge with teams about state machines. We are the Crazy Cat Ladies, 6 girls with an extraordinary love for cats. I hope you enjoy and learn a lot from our presentation. This is a recorded presentation, but if you have any questions, please put them in the chat box and we will answer them. And now we present Schrodinger.
Today we're going to be talking about Schrodinger. Schrodinger is a Java library that our team uses to build state machines and robot control systems. You may be wondering, what is a state machine? A state machine is the combination of a number of states and transitions. A state machine only occupies one state at a time. We named our library after Erwin Schrodinger, a scientist who did a thought experiment on quantum physics involving a possibly dead cat in a box. State machines are very useful in FTC robots because they allow us to avoid code having to stop and wait when certain conditions change. One of the benefits of using a state machine is that it can multitask. They allow certain operations to run during a waiting period, which is great when multiple components are needed to move simultaneously in the robot. State machines are great and especially helpful during teleop. For example, consider a robot that plays tennis. After swinging the racket, the robot driver would like to continue to move the robot while the racket is drawn back again. A state machine can manage the operation of the racket while the robot continuously moves in response to the driver's commands. This code lab will teach you to create an op mode for an FTC robot that uses our Schrodinger library that you can use in your future state machines. For this project, you are going to need a computer that can run Android Studio and an Android phone that can work as a driver station and robot controller. Additionally, you will need Android Studio. If you are new to Android Studio, there is a link to a tutorial at the bottom of the page.
Here we have instructions on how to get set up. If you do not have Android Studio, we have provided this link so you can install it. As Audrey previously mentioned, you have to use Schrodinger in Android Studio. OnBot and blocks will not work. If you are familiar with Git, you can create a clone of the FTC repository on your computer. If not, we have provided a link here on how to do so as a zip file.
Now you're going to need to add Schrodinger to your project. To do this, you'll have to add Crazy Cat Lady's Maven repository. This lets the Android Studio Gradle building system know where it can download the Schrodinger library. Add the Maven URL ending in crazycatlady/maven to the repository section at the bottom of the build Gradle file in the root folder of your project. After doing this, your code should look like the code displayed in the dark gray box on the screen. Next, you'll need to make your project dependent on Schrodinger and therefore cause the Gradle to download the library. You will need to add implementation FTC Crazy Cat Lady Schrodinger 0.11 to the end of the dependencies section and team code build release Gradle. Once again, it should look like the code in the dark gray box. Schrodinger uses Java 8 features, so it's important to enable Java 8 in the code. To do this, change the compile options section and build common Gradle in the root folder of the project. You will now need to update the Gradle by clicking the Sync Now button that appears in the yellow bar towards the top of the screen. It might take a few moments to fully sync. You'll know it worked when you can see the Schrodinger external library in the project view of the project window.
Now we are going to create a teleop mode that uses Schrodinger. First, create a new Java class called Schrodinger teleop mode. You're going to start by adding basic code that will display the X and Y values for the left stick of Gamepad 1. This is shown in the code below. Keep in mind that this is not true Schrodinger code. This is just to make sure that all of your elements are working and that you can correctly create an op mode. Next, we're going to add a state machine to the op mode. This is going to include a 5-second countdown when the A button is pressed on the gamepad. First, at the top of Run Op mode and above Wait for Start, we're going to declare the state machine SM and initialize the data logger shown in the gray box below. Then, after wait for start, add the initialization of the state machine in this block also shown below. The code above is explained in these following steps. It is going to first instantiate a new state machine object. It is going to add a state that only exits when the A button is pressed. It will also add a state that counts down according to the number of seconds specified in the context. It is going to set the state machine to loop so that it goes back to the first state after transitioning away from the last one. And it is also going to initialize the state machine and provide the number of seconds that it will count down with via the context variable. At the top of the while loop, add state machine.run to repeatedly run the state machine, and notice when you run the op mode that the stick telemetry feedback will continue during the countdown. The entire class is shown below in this gray box of code.
You will now be creating a more complex state machine. You will do this by using a jump to create a loop. One of the benefits of Schrodinger is that it allows state machines to have internal loops using the jump transition. The code below replaces the initialization of the state machine object to add some additional complexity to our countdown. The third state will jump back to the previous state 50% of the time to repeat the countdown. You can imagine this is beneficial for things like state machines needing to recover automatically from some sort of failure. Complicated state machines can be created that are defined more by the jumping transition than by following a certain sequence. For example, a state machine that can transition between any 4 repeating states could be implemented with 12 jumps.
In the previous examples, the state machine is initialized with a number of seconds as a countdown. In this specific instance, the context for the state machine is defined as an integer. However, it is possible to create your own, much more complex data types and complex data sets for Schrodinger state machines, such as arrays, hash maps, etc. See below for an example where we have defined the class state machine context and defined it in the initialization of the state machine. In this example, data is collected in the first state and is then needed again in the third state. A state machine context object is used to store the number data in the widget detected field. You can imagine a real-world example of this where a robot uses a sensor to read a clue on the field that defines the location of a game element, which the robot then goes to retrieve. For example, any of those who are familiar with the relic recovery game remember that Vuforia was needed to decode a picture to determine glyph placement. For example, notice that the second state in this state machine is created using the pause function. This makes it easier to create a state that waits for a servo to complete its movement. One of the benefits of Schrodinger is logging. As shown in the code below, a history is recorded of each execution of a step with timestamp information and the string representation of the state machine's context. The context is not printed again until widget detected has changed in order to decrease the amount of redundancy in the log.
Have you ever wondered how you win the Motivate Award? Well, Boombots told us just that, along with how they were an Inspire Award winner. A boss from Boombots did an incredible job telling us about the different kinds of outreach and how to effectively present this information in your engineering notebook. He started his presentation explaining the advantages of short-term versus long-term outreach. Short-term outreach usually consists of a couple of events which promotes your team and first, while long-term outreach usually consists more of teaching people and spreading STEM knowledge. An advantage of long-term outreach is that you can witness the growth and development in people as you work with them. Also, as your team plans their outreach, focus on how your outreach can leave a lasting impact on people. The next type of outreach a boss touched on was virtual versus physical outreach. While physical outreach is more beneficial, virtual outreach helps you get your name out there to a wider audience. Physical outreach is more impactful to people who are less familiar with STEM, while virtual reaches more people, so it is easier to convey information. He gave us an example of his involvement in First Updates Now as a virtual outreach. The last type of outreach discussed was local versus international outreach.
He told us while local outreach is very direct, international can be just as beneficial and can set your team apart. All of these valuable achievements can get lost without being well presented in the engineering notebook. Abbas next told us all about Boombot's notebook, which we noticed is very well organized and easily readable. He gave us some tips on how to format notebooks so the judges can easily read over it, such as don't overcomplicate, have small groups of text so it's easy to read, organize your table of contents so the judges can go from section to section swiftly. Also have sections and subsections in your table of contents. But don't take my word for it. Make sure to watch the replay of Abbas's seminar so you can take a look at their notebook, sponsorship bracket, budget, CAD designs, robot progressions, iterations of capstone, and initial thoughts of challenges. A week ago, Nick from SwampBots told us all about their SlickBot, which he described as a custom, highly competitive design. He hopes to incite growth in teams by giving them hands-on development skills. He told us about some of the advantages of their first iteration of SlickBot, which was that it was very modular and there was plenty of space for adding attachments. Unfortunately, however, in order to do so, they had to remove some brackets, which slowed down brainstorming. Another downside is that some of the connections were not very strong. This would not cause the robot to break, however, it would rattle slightly. For their second iteration, they made the main body in CAD, and Nick showed us some of the views of the design. They changed to a 3D printed pulley, peanut and churro bars as well. For their competition robot, they did a mid-season rebuild for some more maneuverability. They switched to peanut and churro bars to strengthen connection and kept their modularity. However, they didn't calculate their chain length, so it was slightly loose. To combat this issue, they made chain tension slots and put Delrin circles, which the chain ran over smoothly.
The neutrinos were the winning alliance captains at state and shared with us some of the practices that made them successful. The neutrinos presentation discussed the importance of improving in different areas throughout your FTC journey. This can take place in the form of constantly prototyping parts. Prototypes help show the strengths and weaknesses of a design and can be improved upon. This causes the final product to be reliable. Even testing to the breaking point can be advantageous at times, so you are aware of the robot's limits before competition. Neutrinos also suggested using the off-season as a time to improve. Reflecting on your previous season is a way to figure out what areas to start working on. Sharpening CAD, programming, and engineering skills during the off-season can be used to save time from having to learn them during the season. For example, building a strong chassis during the off-season allows you to use it during the season. Neutrinos also provided some tips on how to manage your time as a team. This includes making a plan and having a clear goal for what you want your robot to be in the end. The Stormtroopers were the 4th place Alliance captain in the Lawrence Division at state. Stormtroopers' very own JR shared his wisdom of building with unconventional parts, creativity, and a limited budget. He emphasized that using unconventional parts in your robot can give it a personal touch and can save money while still fulfilling the robot's needs. Unconventional parts can include game parts from previous series, materials offered by sponsors, and readily available off-the-shelf parts. Using these parts can help create a robot that stands out among the rest. It can also be a way for teams with less access to purchase parts to use materials that are easy to find or that they already have for their robot. It is important to remember that these kinds of parts should still provide a purpose in the robot. JR also talked about the Stormtroopers' design process. This includes coming up with ideas, prototyping and testing these parts, and then implementing them onto the robot.
Thank you for spending your morning with us. Everyone stay safe and be sure to tune in as SSSSS returns next week. We'll see you then.